This video is about the input and output impedance of a passive RC filter. It corresponds to section 11.5 of the Applied Analog Electronics textbook. What is the problem here that we're trying to address? Well, we have got our filter as a three-terminal device, and we've got a block in front of it here that's driving the filter. And we've got a block afterwards that's being driven by the filter. Now, we can model the block that's driving it with Thevenin equivalent of a voltage source and an impedance. And we can model the thing that's being driven as just an impedance. Let's call this one our load, and let's call this one our source. Now, for the filter to work correctly, we had two real assumptions that were built into the design. And one was that the filter did not really change the voltage coming into it. So if we think about the input impedance of the filter, that's what do we have if we looked at this thing as a impedance from the input to the reference node. So that's the input impedance of the filter. If that is very small, then we're taking a lot of current through here, and we're going to have a large voltage drop across this R source, and the voltage that the filter is seeing is not really the voltage that we wanted to be seeing. So we really want to have that the input impedance here is very much larger than the source resistance, so that there's almost no voltage drop across here. That all the voltage that's coming from the voltage source is being seen by the filter. So that's one constraint on a design. We can also model the output of the filter as being a voltage source and an output impedance. And again, we want very little voltage drop across the output impedance here, so the load resistor sees the voltage that we expected to see across here. That's the thing that was the voltage divider criterion. It says we don't take current out of our voltage dividers. We can't take current out of these passive filters either. So for that to be valid, we need that our load is a lot bigger than the magnitude of Z out. Okay, so those are the constraints really we want to put on our filter so that we can use it safely, that it does what we expect it to do. That's sort of the assumptions we made when we said, oh, this filter does, and we had some calculations about what the filter did. Those filters were those filter results were based on the assumptions that we weren't changing the input by much, and that we weren't taking current out of the output. So that's these two assumptions. That the input impedance is very much larger than the source impedance, and the load impedance is very much larger than the output impedance. Well, what are the input and output impedances? Well, let's take a look at what that filter really is. The filter was a voltage divider. So we had we had one impedance on top, we had another impedance on the bottom going out to our reference node, and then we took this node to the output. Okay, so we can see that the input impedance, which is just what's the impedance between the input and the reference node here, that's just going to be from here to here. That's Zn equals Zu plus Zd. Now, one of these is a resistor and one's a capacitor. But it really doesn't matter which one's which because addition is commutative. So we can say that this is just R plus 1 over J omega C. And whether it's a high-pass filter or low-pass filter doesn't really matter. That's our input impedance. And you notice that if omega is very, very small, so at DC, this is just a resistor, sorry, if omega is very, very large, this is just a resistor. And if omega is very, very small, this becomes an infinite value. Basically, it's just 1 over j omega c. So it behaves like a capacitor at low frequencies and like a resistor at high frequencies. Okay, what about the output impedance? Well, we did have a formula for the output impedance of a voltage divider, and basically it amounted to the Thevenin equivalent here was just these two impedances in parallel. So well, the formula for that, 1 over ZU plus 1 over ZD. And again, addition is commutative, so it doesn't matter which of these is the resistor and which is the capacitor. This is just 1 over R plus j omega c. And getting rid of that R on the bottom, this just becomes R over 1 plus j omega RC. And again, we can check what happens at 0. At 0, it's just a resistor. And as omega goes to infinity, the 1 plus doesn't matter, the R is canceling, you get 1 over j omega c. So this one is a resistor at DC and a capacitor at very high frequencies, the opposite of what's happening for the input impedance. What we can notice is that this is always going to be at least as big as R. So we had a constraint here that the input impedance had to be big compared to the source impedance. Well, we can guarantee that if our resistor, wherever it is a lot bigger than our source impedance. Then we're not going to be taking too much current from the source. Similarly, over here, we needed to make sure that this impedance was very small compared to our load impedance. So, do we have a bound on it? Well, this is always going to be smaller than R. We can guarantee that it is small enough if R is small enough. And so what we end up with basically is that we want R to be a lot bigger than our source, and we want it to be a lot smaller than our load. If that is met, then our filter is safe to use. It's going to do what we expect it to do. Notice that this is constraining on using a passive filter because we need a large load and a small source impedance, and the resistance we have has to be wedged between them. If we've got something where we had, like we picked a mega ohm for our resistance here, for our resistor, then our load would have to be several mega ohms, tens or hundreds of mega ohms, and that may be difficult to arrange. If we picked a very small resistance here, well then our source has to have a very low resistance, which again might be difficult to arrange unless we have an amplifier. What we'll see later on when we do active filters is that we can get rid of this constraint which limits what we can do with passive RC filters. The active RC filters, because they include an amplifier, can really remove most of this constraint. Okay, that's probably enough about input and output impedance of RC filters.